Hey everybody, wanted to talk about chapter one here a little bit. Chapter one should be something of a review for you, but I wanted to start way back so that we had kind of a foundation to build on and make sure that everything kind of made sense and you had somewhere to start. Okay, this is talking about real numbers in chapter one. We're doing section one of chapter one here, and so let's see what we got. Math deals with number shapes, logic, and arrangements. I think you know that. Um, Anything that has numbers in it or shapes in it, like geometry, logic, is part of mathematics and how things fit together work. And the thing I'm interested in algebra in is because you can use variables, and X would be a good example of that, where you could pick a name for a number that you don't really know. Just call it X. How many cars are in the parking lot right now? I don't know. Let's call it X. And then you say, well, how many wheels are on the touching the asphalt? Well, it'd be 4 times X because each car has four, right? 4 wheels. That concept of a variable means that we're thinking abstractly, and that's a powerful thing. You can do a lot of good work with this. Now, I've got shapes drawn here in the middle. Everybody knows what a circle is, and because we know what a circle is, and then we can talk about circles and shapes and stuff. Everybody sees these and recognizes those as triangles because they have 1, 2, 3 sides. You could also count the 3 angles, and there are equilateral triangles which all have the same side. There are right triangles which have a right angle in them somewhere, 90-degree angle. So we kind of have a basis for conversation there. These are all quadrilaterals, four-sided shapes, and some of these fall into multiple categories. Anything with 4 sides is called a quadrilateral. So a trapezoid is a quadrilateral. A square is also a quadrilateral. A square is also a rectangle because a rectangle is a quadrilateral where the top and the bottom are parallel, where you have all right angles, and that makes a rectangle. But if you have all of those properties and all 4 sides are the same, then you've got yourself a square. You got to know what these definitions are before you can have a conversation about shapes. And it's the same way with algebra here. You got to learn the definitions in order to make this work. Some people find that troubling and bothersome and whatever, but it's a specificity that we need here to talk. So here are some of the things. We're not interested in shapes this semester, but if we talk about the natural numbers or the counting numbers, that would be 1, 2, 3, 4, 5. How many pizzas do we have? How many sheep do we have? Somewhere way back there, somebody started counting something, and they started with 1 and 2 and 3, and eventually, we got all of the counting numbers, and all the way up until the time of the Romans, there was no concept of a zero. And so at some point in history, they actually came along and added the number 0 to that, and that made what we call the whole numbers. So I've got a set of n, which would be the counting numbers, natural numbers. If we talk about the set w, then that's everything we had before plus 0 there. Then people started doing banking, and you had $10 in your bank account, and you wrote a check for $20. That's 10 that you owe the bank, right? Or negative. So as soon as you add the negative numbers, now you've got a set called the integers, and we use the letter Z for that, mostly because the word in German is Zahl. That's the German word for number, so that's where the Z comes from. The rational numbers are anything that can be expressed as a ratio or a fraction. And so, if I have the number 4, I could write that as 8/2 or 4 over 1, or lots of different ways, but it's a fraction, it's a ratio, so that's a rational number. 5/8 or -5/8 or 2.74, that could be 2 and 74/100ths, right? So that would be a rational number where I can go back to fractional form, and we call those Q. I don't really know why we use the term Q for that, but that's what a rational number is. And we'll have rational functions this semester, different things that we'll see that we use that name. Irrational numbers are things that cannot be written as a ratio. And I got 3 examples here. There's lots more, but they kind of fall into the same category. The square root of 5 is not a rational number. Now the square root of 4, that would be 2, and I could certainly write that as a fraction, right? So that's a rational number, but the square root of 5 does not ever work out. It just goes on and on forever. It never repeats or terminates, and so that's a different kind of number. You know, if I start working it out, it's going to be, I don't know, 2.1693447. And it's just, I made all that up, okay? Don't believe that. But it never repeats, never terminates. It goes on forever, which a rational number does not do, okay? Pi right here is a an irrational number. A lot of times we'll use 3.14 as an estimate of pi, but that's not quite right, right? It keeps going. It never repeats, never terminates. E is another number that we'll see this semester, close to 2.718, blah, blah, blah. But again, it goes forever, so that would be an irrational number. All right, that's a different kind of set of numbers. When you put these two together, when you put the rational numbers and the irrational numbers together, you get the real numbers. And that's mostly what we want to do this semester. We will dip our toe into something called complex numbers. And I'll show you how that works, but we don't need to worry about that right now. We're mostly interested in these real numbers, which would be all of the rationals and all of the irrationals put together. I got a picture version of that right here. You can see the natural numbers here, 1 to 3. If I add that 0, I get the whole numbers. If I add the negative numbers, I get the integers. And of course, positive 9 was already in whole numbers, was already in natural numbers. So it's kind of inclusive there as well. 0 is a whole number, therefore it's also an integer, and it's also a rational number. The rational numbers would add fractions. See how that one's repeating. I got a 0.45, 45, 45. So that's rational when it repeats. And over here, the irrational numbers never repeat. When you look at that one at the bottom, I don't have a nice, neat pattern. It's 2, 4, 3, 4, 8, 7, blah, blah, blah. Goes on forever and never terminates, never repeats. So that one's a little bit different. And there's all of my rational numbers in the big yellow circle. And here's my pink ones. And when I put those two together, now I've got my set of real numbers like that. I've got one more picture version of this. Here's the good old number line that we did back in, I don't know, 3rd grade or somewhere, right? And you've got your counting numbers on there. You've got the, you know, here's 1, 2, 3. So there's the counting numbers. They are part of the real number set. Here's 0. You put that in. Now you got the whole numbers. You put your negatives in. Now you've got your integers. All right, here I'm slipping a decimal in there. I'm slipping a fraction in here. That would make my rational numbers. And then you've got these oddball irrational numbers like e, like pi, like the square root of 5 would be about here. Okay. And when I get all of those in there, that's my real numbers. Okay. So now we can talk about numbers and we can talk about what kind there are. Here's just some to kind of think about real quick. Square root of 25, we know that simplifies down to 5. Technically, there are 2 of them, the positive and the negative 5. A square root, again, is any number that I can multiply by itself and get the other one. So what can I multiply by itself and get 25? Positive 5 times positive 5 would be 25, and also negative 5 times negative 5 would be 25. So there's kind of 2 numbers built into that. Usually we'll talk about the principal square root, which is the positive one, you know, unless we've got a good reason to include the negative, and sometimes we do, okay? But 5, you know, that would be a counting number. It would certainly be an integer. It would certainly be a whole number. And I can't even spell integer. Whole number, you get the idea. It's certainly in the set of real numbers. Okay, but here's a rational number, for example, not an integer, because it's not a, it's a fraction, and I can't reduce it. I can reduce it, but I can't reduce it to an integer. If I take 3 out of both of these, then that would be 11/3, and I think that's as much as it'll simplify. So it's a rational number, but it's not an integer, not a counting number, not a whole number, but it is a real number. Okay. Square root of 11 would be irrational. And at some point I'll show you kind of a table of square roots, and recommend that you kind of memorize the first 10 or 12 of those. Here's a rational, therefore a real. This irrational would also be, you get the idea, right? I'm looking at this one. It could be a rational, could be an irrational. Can I find a repeat in it? There's a 303, 303. Oh, just broke it. So, technically you ought to look and see if that whole thing repeats over and over, but it doesn't, because here's a 333. We don't have any more information. I'm going to put that one down as irrational. It would take a little bit more poking around to be sure, but you get the idea, right? We want to be able to classify what kind of numbers we're dealing with. Now, what can we do with these numbers? Who cares if we have numbers? Well, the numbers are pretty important, and we can do a lot of stuff with them, but there's an order to it, right? There's a priority level. There's some steps that we have to go through to get this thing right. And we want to do parentheses first. And so as we go through the problem, and like here, for example, I'm seeing those parentheses. That is the first rung, first priority step right there. And it's good practice to just copy everything else. And then right there, I've got a 2 times 8, and go ahead and simplify that part. 2 times 8 would be 16. Okay, so now I've done my parentheses. I'm looking for exponents. There are not any exponents in that problem. This one has one right there, right? This one has one. But in the problem we're looking at, we don't have any. So I don't need to worry about it. I'm going to go ahead and check that off. There weren't any, but we don't need any. Multiplication and division. I do have some multiplication and division. There's some division, and here's some division. So I have to do that before I do step 4. The addition and subtraction comes last. And I want to do any multiplication and division before I do addition and subtraction. So 64 divided by 16, that is a 4. And 14 divided by 7 would be 2. And 4 plus 2 is 6. So that is the proper answer there. And you can see all sorts of ways that if you didn't go down this list and go check, 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 that you'd get yourself in trouble and you'd have the wrong number at the bottom. So this order of operations is pretty important, and we need to think about that. Let's look at the second one here real quick. I do not have any parentheses, so I'm going to check that one off. Exponents, there is one. We've already marked it. That's the most important thing to do, so I want to do that first. 5 squared is 25. And I'm just copying the rest of this. Now, I really need you to get in the habit of doing this, because I took this first line and I did one little piece, and everything else came down. I've still got the whole problem there. I didn't go off on the side and scribble and do some stuff. It's logical. It's in order. I can see what's happening. Okay, so we have done the exponent. We're looking for multiplication and division. Sure enough, I got some here, got some there. 2 times 25 would be 50. Over here, 6 divided by 2 would be 3, and 50 plus 3 is 53. All right. Don't want to belabor this, but let's do one more. This gets people into more trouble than just about anything else that we're going to do all semester, honestly. So I'm looking for parentheses. That's the first and most important thing to me right now. Let's copy everything else. Now, when you get good and comfortable with these, you can kind of start to take some shortcuts and double up on stuff. And maybe I could have gone ahead and squared 25, 5 and gotten 25 squared and gotten 25 or whatever. But I really just want to kind of do this step by step here. Parentheses, we did it. I'm looking for exponents. That, of course, is this little part. So now is when I should come in here and say 25 minus 4 divided by 7 and copy all the rest of this. 2 times the square root of 9. We've done our exponents, multiplication and division. On top, I've got subtraction. We're not doing subtraction yet, so I can't do this division yet here like that. But see how it's all in the numerator, the top of the fraction? It's almost like there's little parentheses around that. Okay? That whole top has to have the subtraction done, and then I can do the divide by 7. Okay? So maybe this would be a good place to go ahead and do that, as if it's in parentheses. It didn't put them in, but it's understood that has to happen before this division can happen. 25 minus 4 would be 21. So I've got that. Here I'm copying the minus 2. Ooh, square root of 9. That works out to 3, right? So we could have done that here on step 2. There is a way to write the square root of 9 as 9 to the 1/2, express it as an exponent. We'll be looking at that, so don't worry about it too much right now. But if I go ahead and do that step 2, 21 divided by 7 would be 3. And then I want to subtract 2 times 3 is 6. Notice I'm doing this division. I'm doing this multiplication because that's all part of step 3. Now I've got a 3 minus 6, which would be negative 3. And maybe you find that tedious, but you know what? It's worth it to get the right answer. And if you don't go through the steps, if you don't copy everything down and follow it logically, you will not get the right answer. And when people have problems with math, it's because they didn't keep the rules. All right. Here's some more rules for you. These are called the properties of real numbers. I don't know if you've ever played chess before or not. I don't really care for chess, but some people really, really like it. So I got a chessboard up here, and you can see the rules of how these things move around. This is a rook, and a rook can slide as far as it wants horizontally or vertically, while a pawn can only go 1 space or 2 spaces forward, and the queen can move just about anywhere. The knight has to go 2 steps in 1 or 1 step in 2. And so on. The bishop goes diagonally, that kind of thing. Knowing how the chess board works and how you can move your chess pieces means that you get to play chess. Knowing how numbers work and how they get to move, their moves, if you will, means that you can work with numbers. So right here I've got a number of these properties. The first one is called the commutative property. And when you commute to work, you're trading places, right? You're going from home to work and then back work to home. Well, that works with addition. And if I have two numbers, A and B, let's just make up some numbers here. If I had 4 plus 3, I think you would agree that that would be the same thing as 3 plus 4, right? I can commute. I can change the order of those. And for both of those, I'm going to get 7. It also works for multiplication. If I take some number 2, let's say, times 3, that's the same thing as 3 times 2. Both of those would be 6. So this property of real numbers, the commutative property, where I can commute, I can change the order, is going to hold in my two operations here. We call the things that we can do operations. All right. The associative property says that if you have 3 things, first number, second number, third number, it doesn't matter if you add the first 2 and then add the third one, or you could add number 2 and 3 and add this one, right? And we could come up with some example, 1 plus 2 plus 3, like that. If I do these first 2 first, I'm going to get 3. 3 plus 3 is 6. And then here, using those same numbers again, 1 and 2 and 3. This time I want to put those together. 2 and 3 is 5. 5 and 1 is 6. Okay? So I can associate. I can move these things around. The order here doesn't matter as long as it's all addition. Okay? Or I can do the same thing with multiplication over here. And I can, multiply. I could take 1 times 2 would be 2. Multiply that by 3. 2 times 3 is 6. And then over here, I could take that 1 out here, and 2 times 3 would be 6, and 1 times 6 is 6. So I can move those around. Have a property called the identity. And this is an interesting one. There's an additive identity. All that means is that if I add the identity, if I take the additive identity, which is 0, and add it to some number, I get the identical number back, right? 5 plus 0 is 5. The identity didn't change it. In multiplication, the multiplicative identity would be 1. And all that means is if you multiply by 1, then you didn't change the number. 14 times 1 is still 14, right? So that's a property. Inverses. If you take a number and add the negative number, you're going to get the additive identity again. If I do it with multiplication / division here, a divide by a or multiply by the inverse of a, again, I'm going to get the identity right there. So those inverses are important. Sometimes, like let's say we've got a algebraic expression 3x plus 2 equals 0. You probably already know that first thing we would do is come in here and subtract 2 from both sides. Why? Because it's the inverse. Here's plus 2, and if I subtract 2, those are going to cancel, give me the additive identity, 0. Okay, adding 0 doesn't do anything, so I can forget about it. And then the same thing down here. When I want to get rid of the 3, I'm going to divide both sides by the inverse, and I'll get my answer over there. We're going to do more of this, so don't worry about that. But this is kind of the background, the backbone of what we're trying to do here. Got one last property I need you to have seen. Here, if I take some number outside of the parentheses and I multiply by some stuff that's added inside the parentheses, that's the same thing if I take this first number times the first one inside, also multiplied there. Okay, so a times b would be ab, a times c is ac, and if you want a little example here, I could take 2 times 3 plus 4. When I just do this straight, 3 plus 4 would be 7. So I'm really doing 2 times 7, which of course would be 14. And somehow I'm out of room here. I'll put it up top, all right? And then what they're saying is I could take that 2 times the 3 and add to that the outside 2 times the inside 4. And of course, that's going to be 2 times 3 is 6, and 2 times 4 is 8, and 6 plus 8 is 14. Same thing we got before. The distributive property is really important in algebra because we're going to have stuff that we need to distribute all the time. It might be 3x plus 2, but we're going to take the 3 times the x, and that 3's got to get multiplied by everything inside there. So there's 3 times the first one, 3 times the second one, going to be 3 times 2, that's going to be a 6, and we can simplify this thing down a little bit, break it into pieces, so we can figure out what to do with it. Okay, when we get these algebraic expressions, and when we say an expression, it's just a series of numbers. It's something like 3x plus 2, and when they say evaluate that, they're going to give you a number that they want you to plug in there. Okay, there's no big deal here. Remember that x is a variable. The value does change, and whenever the value is 4, then I can just take that 4 and plug it in there. Right, I've got 3 times x, but now I know x is 4. I'm adding 2, and now I've got a little expression that I can work. And of course, I'm going back to order of operations, right? So again, you got to have that order of operations to do pretty much anything. But if you don't follow it, that's where people get into trouble. 3 times 4 would be 12. I'm adding 2. 12 and 2 would be 14. Okay, so these are easy to do, and but again, the order matters. this looks like exactly the same problem right here, but it's not, right? Look at this one. I've got a 3. There's an x, but they're kind enough to tell me what the x is. So I'm going to plug that in. And now you can see I've got those parentheses. Course order of operations says you need to do the 4 plus 2, the stuff inside parentheses first, which would be a 6. And 3 times 6 is 18. So the order of operations really matters. Here's one over here. This one's a little bit more involved, but again, they're giving us a number and they want us to take -1 and write that everywhere that we see x. So I see x in 2 different places here. I'm just going to drop it in both of those. I've got a 3. X is now -1 squared plus 2 times x, but x is given to be -1. I'm subtracting 4. That is my expression there. It's not really an algebraic expression anymore because I took the x's out, right? Now it's just a thing that I have to chew up with order of operations. And of course, sometimes it helps to just make that little list going down the side. You know, something as simple as this: parentheses first, exponents second, multiplication and division at the same time, just left to right as you come to it. And then finally, step 4, addition and subtraction. I'm sure you've heard, please excuse my dear Aunt Sally, as a mnemonic to remember that by. If that helps, go for it. One semester I had people make up new mnemonics for order of operations, and people had, pigs enjoy mud, dirt, and sand, and, all sorts of crazy stuff. Some of them weren't quite printable, but that's another issue. Get something, and maybe even just write that at the side of the problem until you get used to doing it. Looking for parentheses. I don't have anything inside parentheses that can be done. There's no addition or multiplication or anything inside. There's just a single number there. So I'm going to check off the parentheses. There is an exponent, so I need to hurry up and do that one first. -1 squared. Of course, squared here means take it and multiply it by itself this many times. So I'm really doing -1 multiplied 2 times. -1 times -1 would be a +1, like that. So now I've done my exponents. I'm going to copy the rest of this mess. And I've got that. All right, we're down to multiplication, division. We're going to do that left to right as we come to it. So 3 times 1 would be 3. Over here I've got some multiplication, and 2 times -1 would be a -2. And I've got this subtract 4 hanging on the end. I could put that plus sign there, but adding a negative number is the same as subtracting a number, so I'm going to leave that one out. And now that we've done step 3, it's time to do step 4. And here's 3 minus 2, that would be a 1. And 1 minus 4 would be -3. You could have gone all the way across there with your addition and subtraction, but whatever it takes, that's the answer that we want right there. These algebraic expressions are nothing more and nothing less than making piles of things. So like in this problem right here, you can see that I've got 3 peaches. And if I use the symbol P to stand for peach, how many peaches are there? Well, I've got 3 peaches. All right, so up here maybe we've got P equals number of peaches. All right, and maybe A stands for the number of apples. So, if I'm counting up apples, I've got 2 apples here. Keep going. Here's 2 more peaches. Those actually might be oranges, huh? They look more like oranges now that I think about it, but a little late for that. And here's another apple. And then I've got the number 7 right there. So usually when we get to a place like this and we've got 3 peaches and 2 peaches, it makes sense to put those in the same pile, right? I've really got 3 plus 2. There's 5 peaches on the board there. And I've got 3 apples. And then there's the 7 doing its thing right there. So in simplifying algebraic expressions, we call this combining like terms. We had 1, 2, 3, 4, 5 terms, and we combined all the p terms into a single p term here. Took the 2a and the 1a, put those together to get 3a. And you could see we could go 1, 2, 3, 4, 5 peaches, and 1, 2, 3 apples, and then I've got the number 7 there. So be ready to combine those like terms, but you're really just making a pile of all the same stuff. Here's some of these that we can do. You can see this is a distribution problem. I can't add x and 2 because that's like peaches and apples. They're not the same thing. I can't put them in the same pile. So I can't do anything inside the parentheses. But dadgummit, I can take the 3 and distribute it. That 3 is getting multiplied by that whole thing. And the distributive property says I can take 3 times the first one and 3 times the second one, like that. And so here I have a 3x, and 3 times 2 would be 6. And that's as far as I can go. I cannot put those together. I can't do anything else. That's my answer right there. In this second one, I've got 3x plus 2x, and that's kind of like putting the peaches together. Now I got 5x, and I've got this 4 hanging on. So that's as simple as that one could go. And that's all they want us to do here, just simplify algebraic expressions. This one's a little more involved, but there's an x squared. I can't put x squared and an x together, so I don't really have any over here. There's kind of this mess in the middle here. But it's like this first one that we did. There's a distribution thing going on. X and 4 will not combine. They are not like terms. So I'm kind of left with taking that 2x outside and multiplying by both of the things inside. And let's see what that looks like. 3x squared. I take the 2x times x is going to give me 2x squared. And then I take that thing outside, multiply by the second one. And 2 times 4 would be 8, and I've got the x still multiplied there. And there's a 7. Okay, are there any like terms? Well, I've got x's in these first 3, but that's x squared and this is x squared. That's my peaches, and this is my orange right there, apple, whatever, banana. So, I can put these ones together because they're both x squared. So I'd have 5x squared, and here's a 4x. And then I've got that 7 left over, and that's my answer. That's as far as that one will cook down like that, unless we try to factor it or do something else. Okay, for right now, we're done with that one. All we did was combine like terms, did some distribution, followed the order of operations, kept everything looking good here. Now, you have definitely should have solved some algebraic, I'm going to scratch this word out, not expressions, but equations. And the thing that is different here is that equal sign. An equation says that everything on the left is equal to everything on the right. That this stuff is the same as that stuff. I don't know if you ever had a old scale like this. You've probably seen them though. These used to be really important for commerce. You go to the market and they put some apples on one side and a weight on the other side, and it tells you how much you owe for your apples, right? We don't really do that anymore. But algebra basically says if I put 3x plus 2 on this side and I put 12 on this side, it balances. They are the same thing, the same weight. And what that means is if I take 2 off of the right-hand side and take 2 off of the left-hand side, if I subtract 2 from both sides, then it's still going to balance. Now, I left out these parentheses, so let me get those in here before I get myself in trouble. You got to keep up with all these little marks and everything. So what we want to do is to work this thing and move things around until we get down to x equals some number. We don't know what that number is, but that's what we want to do. And that's what solving an algebraic equation is all about. You see the equal sign, you go for trying to solve it. If it said 3x plus 2, and we'd like you to substitute in x equals 6, into that or something, that's evaluating the expression, whereas we want to solve the equation. All right. Like before, we can't put the x and the 2 together, so I need to distribute here. And 3 times x would be 3x, and 3 times 2 would be 6. And there's a 12. And now, the only real trick to this is you can do anything that you want as long as you do it to both sides. And remember, the goal again is to get down here where x is all by itself on one side and there's nothing but a number on the other side. Okay? Again, you can do anything you like, but you got to do the same thing to both sides. If I divide this by 3, then I got to divide this by 3, right? And, you know, I got to keep that thing balanced up, so I got to do the same thing to both sides. Right here, that plus 6, be real tempting to come in and subtract 6 from that side, and now I'm just down to 3x. That's one step closer to having x by itself. If I do that, I got to do this too, though, right? Again, keep that thing balanced up. When those 6's cancel out, nothing but 3x on the left-hand side. 12 minus 6 would be 6. And so I'm closer. I'm not there yet. But if I were to come in here and divide the left-hand side by 3, again, trying to get the x by itself, that 3 is in my way. I want to get rid of it. I see that these are multiplied together, and I know the opposite is division. So if I divide this side by 3, then the 3 on top will cancel the 3 on the bottom. But now I got to do the same thing over here. All right. So now I've got it to where x is all by itself. The 3's are gone. The 2 is gone. Everything's gone. I moved it, right? But over here, 6 divided by 3 would just be 2. Okay. So that's the answer that I'm looking for. And now we have solved that algebraic equation and gotten x by itself. We want to be able to do that in our sleep. And so I've got 2 more examples I'll rip through here, not trying to hurry you up. But if you have a question about these, ask it when we have Zoom meeting, and let's do a bunch of these if you want. Right there, I combined some like terms. You're trying to simplify, cook this thing down. I want to get rid of that plus 4. The opposite would be to subtract 4. Again, I can do anything I like as long as I do it to both sides, and the goal should be moving it towards having x all by itself. I've got it down to 5x on the left. This is all gone. I canceled that. 14 minus 4 would be 10. Got to get rid of the 5. These are multiplied. The opposite would be divide. So if I divide by 5 on the left and the right, then on the left-hand side, I've got nothing but x. When these guys canceled out, that's what I was looking for. On the right-hand side, 10 divided by 5 is going to be a 2. And we're done with that one right there. This one's a little more involved. Let's see what happens, though. I can't combine anything inside the parentheses. I'm going to distribute right there. I got a 3x squared. 2x times x would be a 2x squared. And 2x times 4 would be 8x minus 7 equals 9. Ooh, boy. Here's a couple like terms. Let's get those in the same pile. Got an 8x. That doesn't go with anything. There's a negative 7 here and a 9 on the other side. Might be nice to put those together, right? Because that would put all my numbers in one pile. So we'll do some more of these. But if I were to subtract 9, and again, I got to do the same thing on both sides, then I'm going to get 5x squared plus 8x, and that's going to be a minus 16. There's a 0 over here. 9 minus 9 cancels, and I get a 0 there. So this is going to be one that I'm going to try to factor here. We've got a whole section on factoring coming up, so I don't want to belabor this point here. Let me see if I'm going to poke around and see if I can get a solution to this real quick for you. But let's try a 5x times x. Right here, I need something in the first times the first would give me the first there. So 5x times x would give me that. Back here on the back, I'm looking at this negative 16, and I need something here and here that are going to multiply to give me negative 16. 4 and 4 would do that. If I put a 4 and a 4, that's going to be 20 minus 4 is 16. And I need an 8, so that doesn't work. And we're just going to kind of poke around. What about a 2 and an 8? That would be a 10 minus 8 would be 2. You get the idea. We're going to have to chew on this one a little bit. And I've got, this is what we call a quadratic equation. Once we get it down to this form right there, and we've got a whole section on quadratics coming up. So we don't need to worry too much about this one right now. But somewhere out there, there are actually two numbers. When we have an x squared, you're going to get the first number and the second number. Both of those will satisfy that equation. And let's not worry too much about that today. We'll come back and do a bunch of this. This is the last slide I have for you right now. Today, I normally teach physics here, and I'm just teaching math because I need something else to think about, and it's kind of fun and gets back to my roots. And but these are some formulas. You don't need to know any of these, okay? But all of these come from physics. This talks about motion, how things move. So if you're on your bike or on your car, you're moving at some velocity for some period of time, and maybe you're speeding up, you're accelerating for that same time. It tells you how far you go. That's a formula. That's an algebraic expression, a math model, if you will, that says how things move. Right here, this is how gravity works. If you've got the Earth and the Moon, or if it's a banana and a paperclip, it really doesn't make any difference at all. And there's some distance r apart. You can calculate how much gravitational force will be between them. Look at all these beautiful variables, g, m1, m2, the mass of the first and mass of the second one, r, the distance between them. How fast does heat move through a material? Hot over here, cold over here. I got a formula for that. I got a mathematical algebraic model that says the heat per time is going to depend on what the material is. Is it aluminum or glass or brass or gold? What's the cross-sectional area right there? How big of a chunk are we talking about? What's the difference in temperature between the hot side and the cold side? And how far does it have to go? And all of those variables get mixed in. And algebra is just so beautiful, so wonderful, because it gives us a way to solve all these problems and think about things, how the universe works, when otherwise we wouldn't have any way to do that. So again, you don't need to know any of those formulas, at least unless you come take physics from me. But I just think they're good examples to go, sometimes people go, well, I got to know this. We need scientists in this country. We need engineers. We need people that are building things and making things. And you got to know the math behind how it works. And I want to see you finish school and go do great things. Go, figure out how to save the planet or something, right? And it all comes back to this algebra. So it's really good stuff. Anyway, thanks for listening, and please write me email, a text, something if you have questions or if there's something I can do for you. If you have questions, it's also good to make a list of those. And when we do the Zoom meeting, then just bring those questions up. You can just ask me in the Zoom meeting, or you could text them. There's a little text service within Zoom, and you just drop it in there, and I'll answer the question, okay? So the Zoom things are all about asking questions, getting answers. How do I do this? I got stuck on this problem, and we'll figure it out, all right? This stuff isn't that hard. You can do it, and I want to see you succeed and do really well in this and in everything else. Thanks. Have a great day.